Welcome everyone. It is the Hive community meetings again, and today we welcome Professor Anna Klimovic from ETH Zurich, Switzerland, who will introduce Dandelion, a platform which redefines function as a service with a new cloud programming model, which composes pure compute and I/O functions in an application data flow to optimize cloud systems performance and resource efficiency.
So this talk is going to be about looking at serverless computing through a bit of a different lens, given the context of how software and hardware have been evolving. We're going to look at considering a new programming model for serverless computing, and then accompanying with that a new execution system for how lightweight functions can execute efficiently in the cloud. So to kind of set the stage here, I'll just kind of briefly talk about the evolution of cloud computing, because it's part of what motivates us to even consider a new programming model. So increasingly, the cloud is evolving from this model of users renting virtual machines and having, these catalogs of CPU, memory, storage configurations that they need to choose from, to building applications on top of elastic compute and storage services that are operated and offered by the cloud providers, right? So AWS Lambda is just one example here, but typically your application consists of a whole ecosystem of different storage services, database query services, perhaps even some machine learning as a service platforms. And so increasingly, this old model of we need to make the cloud appear like just a bunch of virtual machines to make it easy to migrate workloads from on-premise is not as important today, because a lot of workloads are actually being built cloud native. They are designed to work in the cloud. And increasingly, the way cloud providers and platforms are differentiating themselves is by offering these kind of managed elastic compute and storage services. And starting to emerge, what is the right question that's kind of starting to emerge, and I think is a good research question to be exploring, is what is the right programming model to build applications that take advantage of these services, as well as how to build each of these services itself so that the overall application can be efficient, but also easy for users to develop and reason about. And so the kind of common theme of what these elastic compute and storage services are providing is that they're raising the level of abstraction to the cloud so that the user is no longer explicitly provisioning, scaling CPU, memory, storage, right? Under the hood, all these services, what I mean by elastic is in some way they're auto-scaling based on the actual load. So the amount of data that needs to be stored or invocations that signal some computation needs to be done. And then the billing model here is that users are charged based on the amount of resources consumed, which is scaled based on the amount of load the service received. And so this is, as you're probably already familiar with in this audience, what we call the serverless paradigm. But I want to emphasize this functions as a service is just one example of kind of the larger serverless paradigm idea. And so if we step back, kind of what are the opportunities, why is it, what is serverless? What is exciting about serverless? I think one of the really important opportunities is that it makes the cloud more accessible to non-experts, to non-systems experts, because these complexities of managing the cloud infrastructure are hidden away. And serverless today, in particular, functions as a service, presents one type of programming model that hides this resource management. But it's still an open question of what is the right way to hide infrastructure management and enable users to build cloud native applications with some sort of higher level of abstraction than just turn on a machine and deploy my application inside there as if it was on premise. The other important opportunity, and I think this is especially one where there's a big gap today in terms of opportunity and what's happening in practice, is optimizing the efficiency and performance under the hood, right? In theory, because the cloud provider is now in charge of auto scaling, the cloud provider is the one that gets to see, what resources are being consumed and can see also a global view of what different users are doing. So ideally, if everyone's leaving the resource management to the platform should be able to do this more efficiently and provide higher performance for all its users, right? But in practice, the way serverless runs today, is actually very inefficient in terms of how it utilizes resources. And we're going to look at some examples and talk about, how we can sort of fix that gap. Right, so let's zoom in a little bit more from the opportunities of serverless to the realities today, and then discuss kind of opportunities to fill that gap. Right, so I said that there's a huge opportunity to optimize the efficiency, how well utilized the CPU, memory, storage is under the hood, and the performance of applications with serverless, because ideally the platform can make these auto-scaling decisions well suited to what the application actually needs. Okay, but in reality, the system stack is kind of several steps behind. It's kind of still the legacy infrastructure stack that the cloud has been using for a long time. And it turns out that, if you're using the system stack to manage really small, short-lived tasks, you can expect to see some significant overhead, right? So one example is that serverless tasks each need to be isolated, right, for security reasons. And the common approach to doing this is to run each task inside of a virtual machine. Now, it's not kind of the typical virtual machine that you would boot if you're using infrastructure as a service. Instead, sort of the FaaS infrastructure has kind of chiseled away at this VM implementation and come up with a more lightweight implementation and design, often, for example, called a MicroVM, right? But still, it's sort of taking the original idea and retrofitting it in some way. But we're going to see, even with these MicroVMs, it's still non-negligible, the amount of time they take to boot, the memory overhead they have, if the type of task you're running in there is a small and short-lived task, which is typically, one of the goals of serverless is to support very fine-grained tasks, so users can pay for just small amounts of computation they need. Okay. Another example is taking kind of a legacy, kind of very popular cluster manager like Kubernetes and not chiseling away at it, but building layers on top of it. And an example here that we'll look at very briefly towards the end of the talk is taking Knative, right? So essentially, the vHive stack is combining Knative Kubernetes and building the functionality to orchestrate these virtual machines that run the tasks in a cluster. Okay. And functionality-wise, this makes a lot of sense, but we'll see that it also has some performance penalty because the underlying system here, Kubernetes, was not designed to manage really fine-grained, short-lived tasks. And then the other thing that I'm going to end up touching on is more about the programming model, right? So these two examples of the VM and the cluster management stack, this is more about how to build the system layers and optimize their performance. But there's also the question of how does the system layer interact with the actual way the application is designed? How does the user actually specify their application, right? And the current programming model in serverless computing basically treats each of these separate serverless functions as a black box, right? It's really opaque, the interface between the application and the platform. The platform doesn't know what data this function is going to fetch until that function actually starts executing and starts, asking for data from S3, for example, right? The function also doesn't really know how much compute is going to be needed. The user just needs to specify some hint about the memory, and then the platform is sort of guessing and adjusting compute as proportionally, right? So this is kind of the choice that's made today, and again, it sort of comes from the retrofitted model of cloud computing so far has been built around this principle of just taking opaque user applications, putting them inside of virtual machines and letting them run. But if now we're abstracting the whole interface to the cloud and users don't need to be the ones that are manually turning on and off their VMs, we have an opportunity here to both rethink what we're running the tasks in, should it be VMs, and what is the interface? How should users even specify their applications? Okay, so that's kind of what I want to touch on today. Right, so let's start by looking at sort of this, I mentioned there's some overheads that come with even MicroVMs. So just to sort of demonstrate this in practice, I'll show you the results from one of the experiments that we ran, where what we're running here is a Firecracker server. And we're running matrix multiplication as an example micro benchmark. We're doing a 128 by 128 integer matrix multiplication. And we have a front end here that's receiving HTTP requests, and we're plotting here the requests per second versus how the tail latency behaves as a function of the load on the server. And the first line I'm actually going to show is what happens if I take away all the firecracker stuff, and I'm just showing you kind of best case, if I just locally execute this matrix multiplication bare metal on the server, this is the tail latency I'm going to get. And then I can compute theoretically what's the max throughput I should be able to support, right? So this is kind of best case we could hope for. Of course, if we're going remote, there's going to be some overhead, but also we're running these tasks inside of VMs. If we run inside of hot VMs, which means we assume a VM that has the preloaded code for this application is already available, then we get this sort of curve where we can see already there's quite a big gap to bare metal. But we're going to see that the real problem is actually when you can't assume that all requests are going to go to a hot VM, but rather that at least a small fraction are going to have the booting of the VM on the critical path. Okay, and then we start to see a huge latency impact. We're looking at the tail here, so we are looking at, in particular, the requests that are impacted, but this is an important metric. And we see a significant drop in peak throughput that we can support. Right, and this is a problem because you want to be able to support as much requests per second as possible on this machine that you've deployed. All right, so we want to try to push this throughput as high as possible and get as low latency as we can. Okay, and although this MicroVM is already improving a lot on what kind of a more generic VM would take to boot, there's still some notable overhead here. Okay, so what are the kind of key issues here that correspond to this overhead? So we're wrapping each separate invocation of a function inside of its own virtual machine. So we have to boot that machine in the cold start, and we have some extra memory that needs to be reserved for the guest operating system inside of each one of these functions. The other thing is that it's kind of hard to optimize the scheduling here. Yes, the platform is in charge of scheduling and can decide how to allocate resources. But how's the platform really supposed to know, right? These functions actually are likely to spend a large part of their time blocked on I/O, okay? But users still get charged for the CPU while their application is blocked on I/O, right? Because you're charged for the full execution time of your function. And the platform doesn't know what data you're going to need in advance in the current way of running things. And so the time it takes to actually fetch the data ends up being part of the execution time that you're charged for in terms of CPU and memory resources as well. Okay, on the platform side, okay, so this is bad news for the user in terms of cost. On the platform side, it's also bad news because that CPU is just idle, so it's inefficient use of resources. But of course, the platform can multiplex multiple virtual machines per core. That's no problem. Well, we have to make sure it's safe context switching between different users. So there's going to be some cache and TLB flushing that's necessary to make this secure context switch between users. This has some overhead, but it can be done. But one thing we need to keep in mind is on the provider side, the expense here is that for all the virtual machines that you're multiplexing, whatever memory they need, you actually need to commit and have available, right? So even though you're sharing the CPU, you're sharing it between many virtual machines that each have their own memory allocations, and you need to make sure that you actually have enough space and memory for all of these things if you're going to ensure good performance. Okay, so these are kind of some of the challenges that arise from the current way of running serverless tasks inside of inside of these kind of MicroVMs. Okay, so what I want to ask here is there an alternative that we could go with, right? How could we start to address these questions? And or these challenges, one question we ask ourselves is, do we actually need to execute functions inside of MicroVMs? Does each function actually need its own guest OS and need kind of this entire isolation layer, or are there alternatives? Okay, so what do we actually need, right? What are the things that we can't go without? We absolutely need secure isolation. And what I mean by this is that the users don't trust each other, and the cloud provider also doesn't trust the users. And so, virtual machines are one way of providing the secure isolation, but we're going to look at how we can, if we move away from virtual machines, we need some other way to provide that secure isolation. And then while providing that isolation between functions, we also want to minimize execution time, maximize throughput, and energy efficiency, right? These are kind of the goals, things we're trying to optimize for while having the strict constraint of secure isolation. Okay, so that's kind of setting the context for why we're building why we're exploring and building a platform that runs serverless functions in a different way, and actually also rethinks the programming model. That's kind of actually going to be the starting point that differentiates this new system that's called Dandelion. Okay, and this is work with several students at ETH, including Tom Kuchler, who's the lead PhD student on this. Okay, so actually maybe before I start, are there any questions about kind of the motivation?
So I have a question for you.
Mm-hmm.
Can you hear me?
I
So
can hear you, yes.
yeah, let's take an example where you have caller and callee functions, which are closely related. Do you think, are you in this current programming model, are you having separate micro-VMs for each function, even when they are related? If they
In
are
the current
related,
programming model, which programming model? The one that
of the
AWS manages?
serverless, yeah, let's say it. Yeah.
Yes, so if a function invokes another function, they will still, each invocation is going to be in its own separate micro-VM.
But that is not efficient, right? You could have, at least for the functions that are related to each other, you could have a same micro VM. Don't you think
Yeah,
so?
yeah. But I guess the thing is that each invocation of a function, right? A function can be invoked perhaps by different users, or it depends on what sort of security settings and like visibility you set for a function when you register it. But in principle, it can be invoked by different users. And so the default thing is each function and each actually invocation of that function will usually run in a separate VM. Sometimes if it's the same function and it gets invoked multiple times by a same user, there can be some opportunities to reuse that VM, but these are optimizations that depend on the cloud provider, and there's all kinds of sort of papers analyzing potential security leaks in these cases. So it's a tough problem, but the safest thing to do is to just have separate context, separate isolation mechanisms and sandboxes.
Yeah, thank you.
Yeah. Okay. I can't see hands, but let me know. Just speak up if you have a question.
So quick question, if
Yes,
I'm
okay.
not interrupting anyone. Hi Anna and hi everyone.
Hi.
You mentioned, or I think you mentioned that running function invocation inside a micro VM is slower than running inside a bare metal, right? Or it seems that the latency is higher. Did you get
Yes.
any clues of why is it slower to run inside micro VMs? Is the like hypervisor slowing down execution because of some sort?
So one of the things that's happening here is also that we're going through this HTTP front end and we have the round trip, right? So one thing that we should add to this graph is bare metal, but over the network.
Right.
And this is something that, for some later when I I don't have it in this version of the talk. I don't have these numbers, but this gap reduces if we have bare metal over the network as well. And here we're passing from the HTTP front end into the micro VM. We still end up seeing a bit of a gap in terms of how Firecracker is then passing to each of the micro VMs versus in bare metal, we just directly copy over the data. But that's kind of the main main reason for this difference here.
Okay, thanks.
Cool. Okay, thanks for the questions.
I also have a question.
Okay.
So you mentioned that the cloud service provider and the user, they also between users don't trust each other, so they use VPN to isolate some stuff because of security issues. And then can we actually use hardware support such as secure plate or that are currently really difficult on the
I can't hear you very well, but let me try to paraphrase what I heard from the question. Let me know if this is what you asked. So I think what you said is, regarding the security concerns, can we use new features that are becoming available on processors to provide better security? Is that the question?
Yeah.
Okay, great. Yes, so yeah, I mean, there's security features that, like enclaves, that go kind of beyond this threat model I'm describing here, where they go further beyond where the user doesn't trust the cloud provider either. And then we're talking about confidential cloud computing and so on. That's a bit orthogonal. It's a separate, topic, and lots of interesting research happening there. But also there's some security features coming out on processors, like, for example, Cherry hardware memory capabilities that provide some forms of memory isolation, for example. And indeed, one of our goals that I'll describe soon with Dandelion is to be able to use these kind of new hardware mechanisms that emerge more easily, to be able to switch to using that as an isolation mechanism and have software layers on top that use that hardware mechanism more easily than in today's serverless frameworks, where they're really based on relying on having virtual machines as the form of isolation. So yes, one of our goals is to be able to leverage these things.
Okay,
and you can do this without Dandelion, of course, but one of our goals is, well, let's see, by kind of how we rethink the programming model, part of our goal is also to enable hardware acceleration and use of these kind of security hardware features to help us in the system design.
Okay, thank you.
Okay, great. All right, so then let me describe sort of how, what's the key idea here of how we plan to rethink the programming model. So our key observation is that we can gain a lot of information. We, as in the platform, can gain a lot of information from user applications to do optimal scheduling and get efficient use of the underlying resources if the function has some information about how data flows between different parts of the application. And we can also consider new isolation mechanisms if we strictly separate the part of the application that does computations, okay? And if those computations are pure computations, then we're going to see we don't even need to provide system call support for them. And so we won't have this huge attack surface to the operating system. That's usually a big concern if you're just allowing any arbitrary combination of computation and I/O. Okay, but if we separate computation into pure computations and separate I/O into separate I/O functions as part of the programming model, this is going to allow us to both explore different isolation mechanisms as well as have more information to do smarter scheduling in the background. And so the key idea is we actually, in the programming model, we ask the user to build their application by separating the pure compute logic from the I/O logic, okay, and composing these things. So basically, a Dandelion application will consist of a composition of two different types of functions, okay, compute functions on one hand. The user can upload arbitrary, untrusted code here, okay, but it needs to be a pure function, so it needs to specify declared inputs and produce declared outputs, okay? And we're going to see a main reason we do that is because the Dandelion platform is going to use the information about what inputs this function needs to prepare those inputs in an isolated memory region, okay, for that function before the function starts executing. And then the function is going to be allowed to execute in that context, and it won't be given any system call support while it executes, okay? Meanwhile, to actually build a useful application, okay, you can't just have compute functions, you need to fetch your actual data from somewhere, right? And in the cloud, you need to interact with the world, right? You need to interact with some storage services, databases, etc. Okay, and this is where the I/O functions come in. So a Dandelion application composes compute functions and I/O functions, and these I/O functions, to improve kind of our the security of this platform and isolation story, these I/O functions are going to be code that's implemented by the platform and exposed to users as a library, okay? Because most of the time, the kind of I/O that you need to external services is some form of HTTP GET or PUT request, essentially. So this is kind of our starting point of the I/O functions. Basically, you can do data fetch or data put over HTTP. And you specify, what's the URL you're fetching from or writing to, and you basically combine these compute and I/O functions to build an application, right? So here's a really simple example of a Dandelion application where, let's say, the application you want to execute is some kind of compilation of some source files. So you need to specify, here are the source files that I have available on, let's say on local disk or something. And here's the compilation logic, right? So the green functions here are going to be the compute. And let's say I also need to fetch some library from a remote storage system. Because I need to go outside of the world of this particular application, I need to go and fetch and interact with an external service. I need to use an I/O function, and I'm going to specify the library location, URL, for example. And once I fetched the contents of that library, I can now feed these into my linking function, which is going to produce the executable. And so in Dandelion, you would basically use our domain-specific language, basically a kind of intuitive Python-like language where you would express this composition, right? So you would say that linking takes as input the output of the compilation and the fetch library and executes this code. Okay, you would also have to specify the internal logic of the compute functions, right? So what is this compilation function actually doing inside, and what is the linking function doing? Okay. And as we said, a unique thing that we're going to see how it comes into the security story is that these compilation or these compute functions should be pure functions that do not actually need to invoke any system calls while they're executing. And if they try to, then a fault, Dandelion will report a fault and cancel the invocation of that function. Now you might say, okay, if I'm not allowed to do system calls, how am I supposed to build any, application? Because even a simple thing like if I was trying to do grep is, reading a bunch of files, or the compilation thing here is reading source files that are on disk, for example. And so doing kind of file open get requests is a system call, right? And so the approach we take here is that we provide a custom libc, because most applications are in some way actually accessing system calls through a library like libc. And we provide user space equivalents to these functions that operate. So when you do your file open, what has happened is because you've specified which source files you're actually going to need, Dandelion has preloaded these into memory before this compilation function has started executing. And when you file open, it's actually going into a virtual in-memory file system and reading at the location or the file offset that you'd like. But that operation is actually all handled in memory, and therefore it doesn't actually need to be a system call. But you can still, use libc, and under the hood, if you're using and linking against Dandelion's libc, this will be a user space operation. So that's about how we propose to build and compose applications. The big key difference here is whilst in AWS Lambda, you could have, built this all as one single Lambda that at some point, let's say goes to S3 and fetches the library, but also has the compute function, has the linking function. In Dandelion, the goal here is that the user, or perhaps in the future, this can be done automatically, but for now, we're expecting the user to do this separation, okay? And now the question is, what do we get from this, right? What's the benefit, okay? So let me first tell you how Dandelion will end up executing these kind of composition graphs. And then we're going to talk about kind of the three main advantages that this gives us. Okay, so here's the function execution system. In Dandelion, the kind of brain of the system is this dispatcher. And then we have the compute engines. So you can think of these as CPU cores that are going to execute tasks. And we have memory here. Okay, so we have a request that comes in. And in Dandelion, an invocation request is a request for a composition, right? You don't invoke just individual functions. You invoke, the application to run. And so let's say we're talking about this linking, compilation, and I/O function that we saw in the previous slide, right? We have two compute and one I/O function. They start out all in this waiting pool. And then because we have the inputs ready for the compilation and the I/O function, these go into the ready pool. And in order to make these functions actually ready to execute, the Dandelion dispatcher needs to allocate separate isolated memory regions for these functions, right? And we're going to see that this is where you can use different mechanisms to do this. It does not have to be booting virtual machines. Instead, what we need is we need to allocate a compute resource, and we need to allocate the memory resources for the function, okay? So the dispatcher allocates a context for each of these functions, and it's going to also load the input data, prepare the input data in memory, right? Because these are pure functions here, in the compute case, we can load the contents of what those inputs are inside of this context. And therefore, this context is self-contained. When the function is actually starting to execute, it has all the information it needs. Okay, for the IO function, this one is going to have system call privileges, and the code that is going to be running this system, this IO function, is actually implemented by the Dandelion platform. So it is part of our trusted computing base. So we also need to allocate compute cores for these functions to actually execute, and that's also part of the task of the Dandelion dispatcher. And then when these functions finish executing, we can release their contexts. And an important aspect is going to be to handle the outputs of those functions, right? So these functions also produced an output inside of their context. And the dispatcher has a whole map of this DAG of how these functions relate. And so it knows where does the output of a particular function need to go next. Okay, so for example, the outputs of these two functions are going to be the input to the linking function. And so we need to do some kind of copy or mapping of the outputs of these previous functions into the context newly created for this linking function. Okay, and when this function now gets compute resources, it can start executing, and then we can send the response based on the executable this function produced. Okay, so that's how Dandelion executes one of these application DAGs. And then, sort of, what are the advantages? What's our vision here with why we're even trying to have this separation of compute and IO? Okay, so one of the advantages here is that it opens the door to considering a variety of other isolation mechanisms. Okay, so aside from virtual machines. Okay, because one of the nice things in this programming model is that you've separated, the IO part, which is typically the very tricky aspect to get right, because you're relying on the system, the operating system, to carry out a bunch of functionality. And there's a large attack surface for all these system calls, which are your way of interacting with the operating system. Now, if the untrusted arbitrary user code is just these compute functions, and that you remove the interface to the system that these functions actually have, that they just get this memory context and have no way to escape from it, because there's literally no call, no interface that they can use to get out of that context, then this allows you to consider a variety of different ways of actually creating these contexts. And we've been exploring kind of one of the obvious things, like why not just run functions as processes in that case, was just separate virtual address spaces. I've been also thinking about how to use specialized hardware like cherry memory capabilities, which can allow you to have the hardware check every time you do a load store, are you within the bounds of the context. So the dispatcher can set these bounds, and while the function is executing, these can be checked by the CPU hardware. Okay, another thing we're looking into is WebAssembly. So you can have these contexts be created as separate WebAssembly modules and use this as another form of isolation. Okay, of course, you could do this even without this programming model, but what we're saying here is there's a nice separation here of the IO and the compute functions. And the compute functions are the untrusted part, but they're the part that won't require this huge attack surface of interaction with the OS. So that's for the lightweight execution. The second advantage that we see is that the platform now has information about how data flows between the applications. So whereas before we said the AWS Lambda platform doesn't know what data you're going to need until your function starts executing. But now each function has its inputs predefined, okay? And so we know when a function becomes ready to execute, and we don't allocate compute resources for that function until its inputs are actually ready. And so we can make smarter CPU and memory allocation decisions per machine. And then hopefully on a cluster scale, we can also be more careful about which functions are co-located because we know which ones actually interact and are part of the same DAG. And finally, another advantage is hardware acceleration, right? Serverless platforms today still lack GPU support, and there's many potential challenges here. But one of the nice things with the Dandelion programming model is that specialized hardware is typically optimized for either fast I/O, like SmartNICs, or for fast computation, like GPUs. And it's much easier to offload something to, say, a GPU if you know that that function is just doing a bunch of pure computations and is not going to need to execute some sort of system call. Likewise, if you know your task is doing pure I/O and not much computation, it's easier fit to just offload to a SmartNIC. So there's still many challenges to figure out here and how to integrate various hardware accelerators under the hood in serverless efficiently. But we think that this programming model is a step towards simplifying that, or at least kind of helping with that direction. Right, so here's an I/O function that gets accelerated on a SmartNIC and a compute function on GPU, for example. Okay, so this is the vision. This is kind of a longer term project. So we're gradually making our way into building prototype for Dandelion. We actually have several prototypes at the moment because we've been exploring. The first thing we've been focusing on are these lightweight isolation mechanisms and exploring how we can build Dandelion as a general framework to efficiently schedule and execute functions, but have kind of modular, different isolation backends that you can choose from. So the first one that we started experimenting with was actually this Cherry hardware memory capability extensions that are available on an experimental board from ARM called Morello. So this is an ARM V8 based architecture. And this has this Cherry support where I was saying when you do a load and a store, the CPU actually checks bounds associated with that load and store to ensure you're within the proper memory bounds. And the operation will actually fail if you're not. We can also just do, without relying on special hardware, we can use traditional MMUs and page tables and just isolate functions as separate processes, for example. The nice thing about Cherry is that within one address space, we can have different contexts. Here we have separate address spaces for each function. And we've also been exploring using WebAssembly modules as a form of isolation. So I'm going to show some initial results that we have for compute functions running in Dandelion versus Firecracker. And in these results, I'm going to show results on this ARM Morello board. So our Dandelion prototype we'll be using is going to be this Cherry hardware memory capability based. Okay, so what we see here is we're comparing requests, as we vary the load on the server, we're comparing the tail latency of Dandelion versus Firecracker. And we're starting here with assuming we have, in the Firecracker case, 100% hot means VMs are loaded for this application. And in Dandelion, it means that we have the code and inputs loaded in memory on the machine. We're not reading things from files. Okay, so and you can see that we sort of see similar throughput limit in both of these cases. Firecracker has a little bit of extra context switching at high load, but overall is able to achieve similar throughput to Dandelion. The big difference comes in, and I forgot to mention the workload here again is this 128 integer matrix multiplication. The big difference comes in when we start to consider that some fraction of requests are going to be cold. Okay, and in Firecracker, as we saw before, there's a big difference when we look at tail latency. If even just 5 or 10% of requests are cold, that's a huge hit in the throughput we get and the latency. On the other hand, you might be wondering where the Dandelion lines are. They're actually kind of all overlapped here because booting these Dandelion execution environments, here we're just creating these Cherry memory contexts. It's much, much faster than booting virtual machines. Okay, cold in Dandelion means actually we're still creating the memory context in both the hot and cold scenarios here. but cold means we're also loading like the code from disk instead of having it already available in memory. Okay. Meanwhile, we said, yeah, booting these, even though they're lightweight MicroVMs, this still has notable overhead. Okay, so in particular, we see a 45x latency difference and 5x throughput difference, assuming this 5% cold scenario. Okay, and so this is directly kind of a cost impact here because you sort of choose how many servers to provision based on how much load you can serve per server and how much load you need to serve in total. So with a Dandelion server, you could achieve 5x higher load and therefore reduce cost. Okay. So what we talked about is kind of going back to this picture of minding the gap of current serverless system design. We said that the current infrastructure retrofits what has been out there and used before, like virtual machines. And we said, you know, one thing we can do is separate consider alternative ways of how we run these functions and have lighter weight sandboxes. And along the way with Dandelion, we also kind of addressed this lack of visibility between the platform and the application layer because we expose data flow information to the platform by separating computation and user logic computation and IO logic at the user application level. Okay, so I'm happy to pause here and take any questions. Can you still hear me?
Yeah, of course.
Okay, good.
Questions. So, essentially, you mentioned that you are trying kind of create execution sandboxes, kind of like a process. But essentially, containers are pretty much what that is. So it's more or less
I'm
containers.
sorry, I really can't hear you well. Maybe.
This is
let me
better?
try. Yes, that's better.
Okay. So you mentioned in your presentation that essentially you are trying to make execution parts more like processes in the system. But containers are pretty much processes with additional isolation. And how does your system compare to containers instead of firebreaks, which are MicroVMs?
Yeah. So you could use containers. Yeah, exactly. They're processes that have additional sort of additional security limitations. In general, from our conversations with cloud providers, containers by themselves are not considered secure enough. There's things like gvisor that Google has, which add even more security layers on top to the main concern is basically this attack surface to the operating system. And so even containers take a while to boot. And I mean, yeah, so I guess what we're trying to do with Dandelion is build an architecture where you can separate out what is the isolation mechanism you want to use from how do you want to actually, you know, pick which cores are going to execute compute tasks, which ones are going to execute IO tasks, how to schedule these things efficiently with knowledge of which tasks can run to completion, which tasks are going to block and need IO, but that we can overlap and stuff. So I would say we're not trying to beat a particular, you know, mechanism like containers, for example, but for us, we see it as it's one thing, if that's what you choose to use as your isolation mechanism, we'd like to be able to make it easy to plug that into the Dandelion framework so that, you know, if you're willing to adopt this programming model, you can benefit from the knowledge you get of separating compute and IO. And hopefully you can get some better security from the container because you also, for the compute functions, know that you won't actually need this interface to the OS. And for the IO functions, you can choose how you want to handle that. You could also choose that, you know, your IO functions should be isolated more securely than compute functions or other way around, or depends on what your needs are, basically. So I would say, yeah, the goal is actually to support a variety of different kinds of isolation mechanisms, and containers can certainly be one of them.
Yeah, thank you.
So one quick question. So how using these user libraries instead of system calls, is it giving any benefit to you in terms of performance?
Using what instead of system calls?
User libraries. For example, you have used certain for libc, you have used a user library, right? So did it give any performance benefit?
Right. So this is a more complicated question. The performance benefits are gonna, like, where we're expecting them to come from is the fact that this programming model enables us to use more lightweight isolation mechanisms that can boot functions faster. Okay. And we're not expecting that when the function executes, the computation will somehow run faster because of the libc. But it's more that we'll be able to boot the context for that function faster. The other thing is we're hoping that with knowledge of which tasks are compute, which tasks are IO, we can do smarter scheduling of CPU and memory resources. Okay. And we're still, to be honest, working out, what to what extent, and these are kind of the advantages that we're expecting. And so far, we've verified the experiments I showed. Let me just pull that up. Here we're verifying this, boot efficiency, that with we can get much lower boot latency and therefore support much higher throughput. But this is just for simple compute function. What we have to look into next is what happens when you're building more complex applications. You have flow of IO and compute functions. And with Dandelion, the trade-off is, yeah, you can boot your functions faster, but you're also going to have more of them because you have to separate things into compute and IO, and what's the overhead of managing those. And so this is something we're still evaluating and analyzing the trade-off space for.
Thank you. Thank you for it.
So quick question, Anna. So how easy is it to decouple IO part from CPU part in applications? And maybe a second part is, do you think that virtualizing the system call layer or when do you think that virtualizing the system call layer is the right approach? And even if the system call that we have, or set of system call that we have today, is the right one for the cloud computing that we have right now?
Okay, so first question, how easy is it to separate? So the real separate, so you can do the local IO stuff, you can, like, local reads and writes to disk, the libc can abstract away for you, so you don't actually have to separate at so fine grained a level. Really, the separation needs to be for when you go external, when you're talking to some external service over the network, basically. And so I think so far, we've been building kind of example applications. It's pretty clear when you're, need to fetch data. It's a, part of your application that you can explicitly, find and separate into. All you need to do is make sure you call the Dandelion IO function to communicate with, and what that Dandelion function can do is, you can put it as input, here's the query I want to run on that database. So this, I think, is not complex,
so you're not relying for,
but it does, it is different. It still requires some changes to your application. In the future, we hope that we could optimize, that we can automate this, perhaps with continuations, or looking at how we can take legacy applications is kind of a whole other research direction in itself, I think. But for building the applications kind of in a cloud native way, in this way, I think it's quite intuitive. Did you have some particular concern of why it might not be?
No, this was really the second question, which is we have looked into system calls for different projects. And virtualizing system call layer is very hard, particularly because there are many obscure system calls with very strange semantics sometimes.
Or if you need randomness and things like that.
Yeah, we can only say what people in the cloud won't use that easily. Like serverless applications may not require all of those system calls or utilize the full POSIX interface. And I was wondering if you have simplified and said, well, this is kind of the minimal set of system calls that currently are available. And everything else is kind of outside the scope. No, this is not allowed in the platform.
Yeah, that's a good question. I think, yeah, we will end up, as we are looking at example applications. I mean, one thing we've done is looking at how to run the Python interpreter, for example, and all kinds of things that it does under the hood. And so as we look at more applications, we run into things where, oh, we should add support for this, or and so on. So I would say I'm not sure the jury is out yet on exactly like a minimal set, but I think it seems reasonable to to have some things where you say, this is the ones that we're going to support, and beyond this is sort of, this platform's not for you if that's what you want to do. I mean, one thing that we have to figure out how to do is accounting for randomness, for example. And you could say you pass it in as an input, for example, if you need a random number that needs to be handled by some platform function that is then going to have as output something that your compute function can get as input. But yeah, we need to sort of figure this out in more detail if you're using inside of your compute function a bunch of libraries that under the hood are assuming they can have access to some of these things. So it's a good question. Yeah, still working on it. Yeah, okay, next question.
Yeah, so my first question is, what is the overhead of data movement between contexts? And if there is a significant overhead, what data movement mitigation techniques have you considered?
Yeah, good question. This is exactly what we're working on at the moment. So yeah, it'll depend on how much IO. So definitely, I mean, what we're doing right now is pretty naive in terms of how we move data. We're basically copying and we're benchmarking at the moment how, what's the impact of this when you vary the IO size, vary, compute amount of compute that happens in between the different chaining of functions, etc. But yes, with copying, this can be quite inefficient. So we're looking into things like how we can leverage DMA engines to do these copies more efficiently, or can we look into remapping instead of always doing copying? Yeah, basically this is active area of optimization right now.
Mm-hmm. And my second question is, speaking of the scaling of the dispatcher, how does what load balancing and fair scheduling techniques have you considered? And for instance, have you considered using separate engine pools for IO and compute contexts? Because that seems obviously
yeah, exactly. So we have dedicated cores for the dispatcher, and this can be scaled dynamically. I mean, currently we just pick something statically, but the idea is that this is something we may need to vary based on the load. And then we have compute tasks and IO tasks are treated separately. For security reasons, you also may want to separate the IO functions from the cores that run compute functions. And so, yes, we have separate pools for IO engines and compute engines. And again, the idea is that this ratio of how many CPU cores belong in which engine pool is something that should be dynamically adjusted based on the load.
Okay, thank you.
You can also have special cores for copying, or yeah, basically at the moment, it's sort of flexible. The cores are in general able to do whatever kinds of tasks. And yeah, we need to figure out what's the right kind of scheduling approach.
And another question that just came up to my mind, have you thought about speculative execution, knowing you have this execution graph, and it seems like some stuff can be executed speculatively?
That's a good point. Yeah, we haven't been doing that. I guess usually you mean sort of assuming you would have some output or some inputs available. That is not yet, but it's, yeah. I guess it depends. In some cases, you might be able to guess. If it's something though, like you're actually needing to fetch from storage and it's the first time you're doing this, then that might be a bit difficult. But if you have some spare resources and you can make some educated guess of the inputs this function is going to need, then yeah, I mean, that could be an option. Yeah, it's not something we've done so far though.
Thank you.
Thanks.
Hi, I have another question.
Mhm.
It seems that Dandelion, the tail latency is much lower until 800 RPS. But is there a reason that Dandelion cannot actually reach RPS higher than 8?
Yeah, good point. So this, I forgot to mention, this is on a machine with 4 CPU cores, where, because we're running this on the ARM Morello architecture, so this is the one that supports cherry memory capabilities, and then we chose to run Firecracker to have a fair comparison. We chose to run Firecracker on this same architecture. So that's why the RPS is actually not super high, because it's 4 cores. And actually, one of the cores here for Dandelion is being reserved for the dispatcher. And it's only 3 cores that are being used to actually execute the functions themselves. So on a larger, we have also some experiments where we run on larger machines with 16 cores or 32 cores, and then we see much higher RPS.
Thank you. There's also a question from Donald on chat.
What is the timeline for
Yeah,
publication of
time
these?
for publication.
Yeah, we're actually working on it. Yeah, let's see. Hopefully in the spring we will be submitting a full paper about the execution system and the IO, the overheads versus benefits of the IO and compute separation when it comes to how these things are passed, chained between each other, and what kind of scheduling benefits we can get. Yeah.
Were you building that on Beehive or something else?
No, we're not building this on Beehive. We're building this, I mean, so it runs on top of Linux, but basically it's a bare metal. It's a, how do you say, clean slate system. So we're building this from scratch. It's a project in Rust in case, yeah. And once it is published, we do plan to open source it.
Thanks.
Cool. I guess, yeah, I won't be looking at the time. I was going to say something very brief about this sort of other side of things, which is the cluster aspect. This is work where we also have kind of a workshop paper at the moment that motivates the challenges. Basically, if you build cluster orchestration on top of Kubernetes, which was not designed for orchestrating short-lived tasks, there's all kinds of overheads that occur in plugging in whatever sandbox you have on the worker into the actual cluster, making the control plane aware of this. And so this is another aspect that we're exploring. And our goal also is, with Dandelion, we hope to make serverless more appealing to a broader range of applications. If you can support hardware accelerators, if you have a much more efficient way of passing data, and if you have information of how to schedule these things, hopefully, a lot of the things that my group is also working on in machine learning side of things, at the end of the day is also kind of about making things serverless in the sense of automating things like GPU scheduling, or how to do LLM serving, or how to train models efficiently and have jobs orchestrated for you. So I just wanted to sort of throw these things out there as other directions that, you probably don't think of immediately as serverless, but at the end of the day, if we can make a platform that enables more efficient computation, hopefully it can also be appropriate for other classes of applications that aren't really suited to serverless today, like ML. So just to conclude, we talked about how users need a more efficient, high performance, and easy to use cloud, and serverless is a promising paradigm because it raises the level of abstraction. But today, the implementation of it is still rooted in this idea of booting virtual machines and operating them sort of opaquely from between the platform and the application layer. So the key idea with Dandelion is to rethink this programming model to give some more visibility to the platform, with hopefully minimal burden on the user, and enable a whole bunch of system architecture optimizations and new designs under the hood. So thanks a lot for having me, and yeah, happy to take a few more questions if people still have time.
Thank you, Anna. It was a really interesting talk, and I think the discussion was really active, which is really great. I think I just wanted to ask one more question. So you mentioned the first part of work is mostly single host part, right? Single host
Yes.
consideration, and the second part is multi-cluster management. Do you see them coming together?
Yes, yes, indeed. Yeah. So, I mean, I think to build a serverless platform, you need both. You need both the cluster story and the per machine. And I think there's a cluster level story for Dandelion architecture. This cluster manager that we've been building doesn't necessarily assume that it's Dandelion worker nodes. We've been kind of trying to build it orthogonal to Dandelion so that it can be used with, something like containers or MicroVMs. But eventually, yeah, the idea is to connect these things to orchestrate clusters of Dandelion workers as well.
Great. That's very insightful talk, and thank you very much, Anna, for joining us. Anna is also one of the steering committee members in the Beehive ecosystem, so there's a lot of contributions from Anna's group, which is really great. So I think we'll continue our cooperation on in this ecosystem.
Yes, and yeah, I have the students to thank for the actual contributions to Beehive codebase and so on. Yeah, so Tom and Lazar, Mihailo, yeah.
Absolutely. So maybe with this, we can open the floor for some open-ended questions like people have the talk, maybe general, okay, any feedback for Beehive, or okay, questions from the community.
I'm happy to also follow up later in case there's.
Can you share more info on how you tackle hardware acceleration? Given that sandboxing and device present challenges. There's a question on chat.
Yeah. So, I mean, maybe I should clarify that what I presented is also kind of a overarching vision for the project. So we haven't yet, finished integrating support for heterogeneous hardware. But we have designed the platform in a way that the abstraction for these engines, for example, is, you can create a CPU engine or you can create a GPU engine that from the perspective of the Dandelion dispatcher, there's some common interface to these things. Okay, and the main point I was trying to make of why Dandelion's programming model can be helpful for hardware acceleration is that if you separate computation and IO, it becomes more clear on what type of accelerator each task should go. So compute tasks can go to, for example, GPU acceleration if the types of computation they're doing is things like matrix multiplication or other things that are well accelerated on GPUs. Versus IO computations, IO functions can end up on SmartNICs, for example. And so I just wanted to point out that the programming model has these advantages. And of course, there's still a lot of systems challenges in how you actually implement this at the end of the day, these engines, and exactly how you take into account isolation. I think our first step would just be to dedicate a GPU to a particular function at a time. But of course, it becomes even more interesting if you're now considering sharing the GPU across many untrusted users and how to do that efficiently. And also modern GPU hardware does have, even enclave support. So there's some interesting things happening in that space. Great. Well, thanks a lot, everyone, I guess.
Thank you.
Okay. Yeah. Thank you all for the questions and also Kiana for giving a wonderful talk today.
Thanks all for listening, and yeah, thanks for the good discussion. Great questions, and yeah, I will, stay tuned for more. It's still early days in this project, and yeah, we will be open sourcing it, and it would be great to have a community around it. And I think there's many directions to go here. So thanks a lot, and See you later.
See you later.
See you.
Bye.
Thank you.